have an unbalanced gender distribution.
So this can be, like, in the case of this paper, gyrification or brain folds.
A neuroscientist started to look at the brain
computers,
as
like
more as an interconnected
it's incredibly negative consequences.
not what I described. Okay, this is brain implants and machine learning for telekinesis. So building a tool to make stuff with your brain. You may have seen this image before. This is Monkey Mind Pong from Neuralink. Monkey thinks that it's playing Pong with the joystick, but the joystick is actually unplugged, and the monkey is playing Pong with like an implant in their brain. And Elon Musk was like, God, Neuralink guys, we're doing crazy stuff. But actually, we had this in clinical trials about 20 years ago. And about 10 years ago, we started doing human trials. So this is a lady who is paralyzed from the neck down. So she's not able to move her limbs, but she's able to talk and smell and stuff. And this was the first time she was able to use an implanted brain-machine interface to feed herself for the first time in years. So this is the power of brain-machine interfaces. Essentially, it's a way to bypass biological signals and get something directly from the brain. So how does this work? It's a system built kind of on 3 components. First, you have to get the signal out of the brain. And for that, we use something that looks like this. It's called a Utah array. It's basically a bed of nails that you stick into the cortex, and each one of those spikes is able to record electrical voltages. So you've heard that neurons are kind of electrochemical machines. This is literally able to record the electrical fluctuations from the neurons. And what you get is for each channel, the voltage around that channel. That's what this data looks like. So then we get this data, and then we have to turn it into some kind of physical meaning. So for example, moving a cursor around a screen or controlling a robotic arm, like that. So of all awesome things, do I care about brain machine? This is my 3rd grade math classroom. My math teacher had 5 of us, and he had like complete free reign over what he was allowed to teach. And so one day he decided to teach us to program in Python. And this was super cool to me because computers were able to do all of the things I hated doing. Like, I hated practicing my multiplication tables. I hated doing algebra, and the computer could do that just instantly. So leverage the super powerful tool so that I could do what I wanted. So you can see, everyone's like participating in the photo, and I'm here in the corner not participating in the fun and just writing my Python script. Yeah, so that's how that class went. But it got me really into computers. If you think about it, why are computers so much better at doing some things than we do? It's because they think in a different way than we do. So our brains are very good at fuzzy intuition, like recognizing, oh, I recognize that, or I recognize that face. Whereas a computer is discrete step-by-step algorithms. So doing math, doing arithmetic, something like that. And so they're not necessarily smarter, they just think in a different way. And we could do a lot more if we let them collaborate. So we've actually been able to do this, and we've been doing it for a long time if you think about it. So for example, computers have historically just been tools to help us do symbolic logic. Like writing down on a piece of paper is really offloading some of that memory so that you don't have to hold it all in your head. And then we develop abacuses and calculators and etc. And more recently, we've also been able to go in the other direction, bringing fuzzy intuition to computers using machine learning. So that is simulating an artificial neural network on a machine to get that kind of intuition. And these 2 technologies have been very revolutionary because they combine these 2 different ways. So if we look at how computers have developed over time, they've gotten more powerful, but they've also gotten kind of more to us. So the trend from PCs to laptops to smartphones to wearables, it's all about the computer being close to you, being accessible. Like a laptop is very handy, but it's pull it out of the backpack, whereas I can just do Siri on my watch to calculate something, and I use that a lot more often. And it doesn't matter if Google has like a data center in Mountain View if you don't have access to it, right? So it's not just about computing power, but it's about how close and accessible that is in your daily life. So when you frame it this way, brain-machine interfaces are the natural end game for computers, because having something in your brain that can help you directly is kind of the most accessible and the most integrated. So brain-machine interfaces are kind of the ultimate computer. They are the closest and most helpful device that you can have. And at that point, you might as well think of it as like a mental exoskeleton. It's something that your brain controls, but it does a lot of heavy lifting. So does anyone have any questions at this point? Silence. OK, great. Oh. No, we're not. Yeah. Yeah. So the question is, can we record faithfully from the brain? And that is a lot of like materials science and engineering that's happening right now. Neuralink, the reason that they are quote unquote behind academia is because they're working on a brand new implant that is, rather than inserting like a giant bed of nails inside, they do thin electrode strands that are thin enough that the brain actually doesn't even notice them. They're about 1/10 of the width of a neuron, I believe. So that is kind of one direction that they're developing. But there's still a lot more to go. There's still a lot of lost information. Yeah. But it turns out that because your brain is so fuzzy and the information is so distributed, we're able to do pretty good at decoding with the very like vague, wide things that we're recording. Anyone else? Awesome. So how do we build this? So you kind of start with a brain, right? And then you have to get the signals out somehow, as Sam was saying. So that's the implant. And then this turns out to be a lot of data. So we can record at higher fidelity, but then that gets to be like hundreds of megabits per second, or faster than your entire house's internet. So we have to compress it somehow before streaming it, ideally out of the brain, to decode it into signals that have physical meaning. So for example, controlling a cursor or moving a robotic arm or something like that. And so these are the three kind of areas of brain-machine interface research. And the state of the field is to make improvements on each of these components, or like a combination of the components. But this is the state of the field. And today, I'm going to look at two papers, one for implant and one for compression, to give you an idea of what research in this field currently looks like. So let's start with implant. You've got this chip, right? So where do you put it in the brain? And specifically, this paper is looking at it. If you're trying to decode speech, if someone's paralyzed and they're not able to move their vocal cords, but they can still try to talk, then where do you want to put the chip to record those speech signals? And what we'll see is that having the chip closer to the output means that the neurons will be firing more in line with something from the physical, so it's kind of easier to decode. It's much easier to kind of understand how muscle moves and then model that in the physical world than it is to understand the abstract, like whatever the hell is going on in your prefrontal cortex, right? Really deranged. So literally, like this is a map of the brain. I give you a quick tour. So back here, we have a lot of sensory association. This is kind of touch. And then here's a lot of the visual cortex. Here we have understanding speech and auditory cortex, so for processing other sounds. And then we have more production and planning up here. So Broca's area works on production of speech. And then there's also the prefrontal cortex, which you've probably heard a lot about. It's like kind of planning and decision making. And that becomes more and more physical through the premotor cortex, and finally the motor cortex. So implant is this big on this scale. So where would you put this square on the brain to get the signals that are going to be most helpful for decoding speech? Literally, you guys can raise your hand and come up and like draw a square here. Come on up, Micah. There's one that the paper selected. Okay. Why did you? So this is not a very good marker. But can you walk us through what you did, what you chose, and why?
I chose here because it seemed like some idea of like production of speech might be useful, but also like premotor cortex sounded like if you were trying to move your vocal cords, maybe that's where some action potentials would go. I really don't have any idea.
Cool. Yeah, awesome. Somebody else want to? Come on up. Eric? Yeah, and then you can go after Eric.
Okay, well, I'm going to draw over here.
Okay.
Because it's near the auditory association area and auditory cortex and like.
All right, so auditory stuff a little bit. Okay, come on up. Okay, cool. So the paper actually selects to put it here. So the auditory cortex is more about kind of what you're hearing. And basically, it's Micah's area, except we also want to be in kind of the primary motor cortex, which is the most downstream area that's directly connected to the vocal cords. And what the paper looks at is essentially, great, we're covering these three areas. How useful are each of these areas signal-wise for the thing that we're trying to decode? So you can see here, this is a diagram of where the scientists put the implant for each of their 6 participants. The green is Broca's area, which is the speech production area. The blue is the premotor cortex, and the purple is the motor cortex. And so you can see they kind of do some finagling to get the implant on each of those areas as much as they can for each patient. And if we look at how effective each area was, we can see that there's actually quite a big difference. So the x-axis here is which area was used for the training. So this is the performance with all 3 areas, and then this is performance with signals just from Broca's area, just from the premotor cortex, and just from the motor cortex. So you can see that the motor cortex had vastly higher performance than any of the other individual cortices, and adding in these 2 cortices for this chart did not improve performance by that much. So the motor cortex is the most useful for decoding speech. Jack?
2 questions. What are the colors and what are the p-value annotations?
The colors are each of the different participants, and the p-value annotations I'm not actually too sure about. I believe it is some p-value on the r-squared. Yeah, I have to look at that. R-squared of the decoded signal versus their training, which is they are able to measure the muscle activity here. Yeah. Yeah, so this is R-squared correlation, and so these patients are not actually paralyzed. They are doing kind of a closed loop training where they have the brain open and they just do the implant, and then they have the patient speak some vowels and then record the activity and then try to match that machine learning kind of after the fact. So they have the ground truth of the vowels that the patient is trying to say, and also the frequency, like the spectrogram of the recording of what the patient actually said. Shar? Yeah. So what do I mean by decoding speech? It's if a patient were to be kind of cut off between their brain and their vocal cords, then they can try to talk, but the signal just won't make it to their vocal cords. And so they're kind of experimenting with a device that you could theoretically implant and then understand what they're trying to say, and then just do what the vocal cords would have done otherwise. So generate the vowels and play it through a speaker. Sophia? So the question is, what level of precision can it be placed? The sensor is about half the width of your thumb, and it's currently for this experiment, it was placed by hand. So basically as good as your neurosurgeon is, and I don't have an actual number on that, but one other thing that Neuralink is working on is they have like a big robot that like clamps your head and then very precisely places the threads in because they have very thin threads. Madison? That was the p-value annotations. So the stars above the bar is the p-value annotations that Jack was talking about. Basically, it's like how confident we are on the different things. I think actually it's like these bars are the 95% uncertainty, and then the asterisk is like footnotes. Yeah, Jenna? Yeah, so this is actually really cool. So when you know exactly about an internal monologue, but when you kind of are muttering to yourself, if you're trying to like copy down an equation or something like that, then you actually get subvocalization. So not only in the premotor cortex, but all the way down in the vocal cords. And so we have had the technology for about 20 years to put kind of electrode pads on the muscles of your vocal cords and reconstruct what you're saying, even if you're not giving them enough air to fully say it out. So this almost isn't anything, like it can't read your mind any more than that could. Instead, this is just able to do it from the brain instead of just from the vocal cords. Okay, I'm going to move on for the sake of time. But the important takeaway here is that with an implant, you don't just need a good implant. You also need to know where to put it. Because different regions of your brain do different things, and placement really matters. And specifically, being close to the motor cortex makes it easier to decode because you're just trying to understand physical movements of the muscles in your throat and not whatever deranged stuff is going on in your prefrontal cortex. So we're reading the throat and not reading people's minds, which is, yeah, that's where we're at right now. So that's the implant. So now we can talk about compression. So the again, we're getting a lot of data from all of these channels from the brain, and we need to compress it in order to kind of make any sense of it. So specifically this paper, which is unpublished research, goal is to help someone use their brain to move a cursor around. And literally, like brain signals, this is their brain, and we want to turn it into cursor movements, right? And surprise, surprise, you do that with machine learning, neural network, and like machine learning stuff. But the problem is that right now this network is like too expensive, and so it has to run on like a PC computer, like a big box machine, and that is very bad for patient quality of life because you have to have a wire sticking out of your head that can get infected, and you have to lug a computer around everywhere you go. So what we would love to do is take this computation and move it to the implant that's already sitting inside their head. So just add a little other chip that does this compression and then streams it over like Bluetooth, which is literally Neuralink's plan, to like a smartphone or something that can do the final decoding. So the constraint here is heat. On a PC, it's great because you can just add fans, add water cooling if you're doing a lot of thinking. On a brain, you can't do that. So we need to stay very low power and compute as little as possible. And the way that we do that is with architecture optimization. So we take our neural network, right? It's too heavy, it thinks too much, so we just get rid of part of it, and we make other parts smaller. And we try this a bunch of times and see how good it can get with this reduced size. So this will decrease accuracy. It also decreases power by a lot. And so it might be a trade-off worth making. And so that's the question of this research. And specifically, this is what I was doing last summer. And so it's like a lot of quantization and sweeps and stuff like that. You can ask me about the machine learning later if you'd like. But the result is we try a bunch of these differently sized models. So like all of these dots are different models. And we see if the trade-off is worth it. So on the x-axis here, this is the computation cost, how expensive it is to compute, and roughly how much power or heat it's throwing off. Then on the y-axis here is the performance of the decoder. So like how good it is at recognizing the brain signals. So what we're looking for is something with low power and high performance. So something that is kind of in the top left quadrant of this chart. So we pick one of these dots and we compare it to the original model, which is this blue star all the way over here. And what we see is we're able to get like an 8 times cheaper to compute model just by losing about 1.5 percentage points of performance, which is pretty good. And it turns out that this is enough to go from, with some other tricks, is enough to go from a computer that you have to lug around to maybe being able to make a chip that will fit inside the patient's skull. So any questions on here?
For like the kind of removing and shrinking different layers of the neural network, is that done like by hand, like human, or is it more like proximal policy optimization, where an AI is itself kind of cutting parts off and rebuilding itself?
Yeah, it's not that complicated. It's just hyperparameter sweeps. So we use kind of Bayesian decision trees. Oh yeah, the question is, how exactly is the optimization done? Is it kind of by hand, you try a bunch of things, or with fancy reinforcement learning? And the answer is somewhere in the middle. We use a basic like decision tree just to kind of look at that. But actually, that is a good thing. That would be a good thing to try here, except for it's a little discrete, so it'd be hard to propagate over. Next.
Is there a path to compile all this inside of the chip rather than like in an external thing, like, even without a wire? Is that possible yet? Or?
So actually, there's so much data that it's very hard to send over anything. So the relatively like low resolution stuff that we were doing over the summer was about 88 megabits per second, which is like maxing out home Wi-Fi. And that actually takes a lot of power. You can't just stick an entire router on top of someone's head. And so that's why we have to do compression on chip before you. Yeah.
Could you also like
So can you expand the size of the chip so that the heat is kind of spread over a larger area? Ideally, we would still just dump less heat. It also makes it harder to implant if you make the chip larger, because it's like harder to hole into someone's skull. And so it's all a bunch of trade-offs. And like ideally, we can just fix it in code and do less computation. Yep. So we have, I can talk to you after, basically, but we just, we have closed loop data because of the way that we train, and so we have the labels, and we can just kind of calculate it. Cool. So that's like some research that's happening in the area of compression. As you can imagine, there's a lot of labs and companies trying to get in on this. And so there's a lot more stuff going on. But this is the kind of research that's happening in brain-machine interfaces right now. And the end game is kind of things we can do. So brain-machine interfaces can improve prosthetics. It's kind of a new class of therapies because it's allowing us to go directly into the neurons of the brain as opposed to having to go like from the arm or something. And you can also theoretically like bridge areas of the brain with one implant that reads on one side and then another implant that reads on the other side. It can also temper things like addiction and depression, because instead of blasting your entire brain with SSRIs, use this to stimulate certain areas to do like kind of like a more targeted therapy. Having better like recording improves our understanding of neuroscience and also of things like machine learning, and trying to take that neuroscience and put it into a chip. So this is one of those things in the cycle that will make the entire kind of scientific machine spin up. And finally, we might someday be able to read not just the motor signals, but also the premotor cortex, prefrontal cortex. And then you can transmit not like what you're trying to do, but possibly your thoughts. And so it'd be like, if I'm working with someone, I'm like vague intuition, like I don't know if this feels right, transmit, and then they're like, oh, like I see what you're saying. Or possibly even Google, like vague, like is this like possible? Like does this exist? And Google might be able to understand that and okay, here's a few things from different points. Because it's essentially where you have to go from whatever's in your head to language, right? It's going directly. So this could be super powerful, I think. I do believe that it is kind of the ultimate computer. But it can also be very dangerous. The Matrix was a good example of what could go wrong. And so the question becomes like, how do you build the legal or economic guardrails or incentives to keep this technology safe?